Well, good morning, everyone. It's certainly a pleasure for me to be here today in Kraków, back in Poland, and a great opportunity to see old friends and hopefully make some new ones. And like I say, it's great to be here. I want to first thank Flexsim InterMarium for creating this conference, and I certainly look forward to the presentations that follow. It looks very interesting, and I hope you find it interesting as well. I also want to thank Flexsim US for supporting my work and supporting my travel here. And most importantly, probably, I want to thank you for coming and participating in this event. A couple of things I'd like to mention before I start is that this presentation will be available, so you don't have to worry about taking notes or writing things down or taking pictures. If you want to, you're certainly welcome to, but we'll make this available. In the interest of time, we may be limited on times for questions, but I certainly welcome to talk to all of you at the breaks or the social time, or we can set up Zoom meetings and chat later. And so I really look forward to your comments and questions. And I will, of course, be here all day today, this evening, and I'll be here all day tomorrow in case somebody wants to set up a time to talk. Okay, so the outline of the presentation today, I'll give you a little bit of background and context. I'm going to talk about teaching two types of courses, one where the focus is simulation, one where the focus is not simulation. In both of those, I'm not going to talk about the technical aspects. What I want to talk about today, a little bit different, is making it relevant to the students and engaging the students in these courses. I'll talk a little bit about some research projects and just give you some ideas in that direction, collaboration with industry, and then wrap up with some final thoughts. So to start this, I'm going to look at the title of my presentation in 3 steps. So the first, teaching, research, and applying simulation. Well, that basically comes from the pillars of what faculty do. Okay. You know, we teach, we do research, and we do service. Okay. And so how do we do that relative to simulation, and how do we combine those and get synergy so we can get more done effectively? The retrospective is from my perspective of kind of over my career, and I think I have a diverse background in terms of academic positions, in that I've taught in business schools in the US and abroad, and I've taught in engineering schools both in the US and abroad. And before going into academia, I worked in industry for about 9 years with 2 different companies, again diverse, synthetic fiber manufacturer and the defense industry. And when I went into academia, I wanted to maintain that contact with industry. And so I've been fortunate to be able to do that. And I listed a few of the companies that I've done projects with. It's a much longer list. These are large companies that you probably have heard of, people like Northrop Grumman and Nissan and General Electric, and some government agencies with NASA and Department of Defense, the Navy and the Air Force. A lot of small companies, but I don't want to dwell on that. I just wanted to mention that that aspect of so you understand where I'm coming from in the presentation. And then I take as my objective today is to basically be this presentation, hopefully, if it's successful, will be a catalyst to help us be more successful in our simulation work. And so what I feel like I need to do is get you to think about some ideas. And then hopefully, at the breaks and other times, we can have discussions. And then hopefully that leads to collaborations. And so that we can work together and be more effective. Okay, so let me drop back and say how far we've come in the simulation world. I first took a simulation class back in the 1970s. Yeah, that's almost 50 years ago. And I started, my first course was in a language called GPSS. And I did my master's thesis using simulation. And I did my first industry project as a result of that work. And what is up there is the first page of my model, my simulation model. That's my model. You might say, well, that doesn't look very interesting. It's hard to read, and that's just the first page. I mean, it was thick. And that's the model. And probably a little bit hard to see, but that simulation model was run using punch cards. Now, it's probably really making me sound like a dinosaur, but anyway, that's where I'm coming from my perspective. I started using flexsim in 2006. So about 16 years now I've been either using it in projects or teaching with simulation. So just compare that to where we are today with flexsim. And not just the graphics and the output, but all the interactions with other technologies. And so where are we going in the future? I'm not sure, but one of the presentations today is talk a little bit about future development. And that's one of the things I've always admired about flexsim, is they have a really great development program. And they're coming up with new ideas and new innovations to make the simulations more powerful, easier to use, and so forth. Now, as I said, we've come a really long way. This is, for those of you that know flexsim fairly well, these kind of capabilities you don't even hardly think about, you just take for granted. But again, I'm relating back to where I started. But I think it's important to understand that the interactions that we can have very easily with spreadsheets or databases, and be able to do statistical analyses, all within the software. Again, when we started, maybe not that long ago, none of that, we basically ran the events and that's it. And everything else had to be done outside. Easily design experiments and run experiments very effectively through the experimenter, and seamlessly connect to an optimizer, or if you want to do your own optimization algorithms, you can easily connect that to flexsim as well. Some of the newer developments, and maybe a little bit more advanced than the ones I listed there, again, is real exciting. To be able to develop, especially logistics and supply chain transportation models on a map, okay, with the GIS. Include agents in your models. We already mentioned virtual reality is set up in the next room, and be able to immerse yourself in your simulation model, and be able to emulate programmable logic controllers. Big topic today is digital twins, and how you can create digital twins, again, using flexsim. And now interconnectivity to other languages like Python, which opens up other opportunities for AI and, say, reinforcement learning. Again, really exciting. So what am I really passionate about today? What I want to do is raise awareness of the value of simulation. And I want to expand that beyond what I call the producers, the modelers and the analysts. I want to go beyond that to what I call the consumers and the proponents. So traditionally, we focus on those producers and educating them. And that's fine, that's good. We need to do that. But I also don't want to lose track, or I want to leverage those consumers, the people that are using it, or that are using the simulation, that didn't necessarily develop it. And those ones that may be just slightly associated with it, make them to be proponents, people that want to do simulation. And so I think that's what I try to do, is how do we do this? The other thing I want to have continued to do is, I think simulation can be a great bridge between education or academia and business and industry. And so I'm always looking for ways to build that. So let me now talk a little bit about the course that focuses on simulation. So that's, from what I'm used to, it's a one-semester course. It's required of all students, say, an industrial engineering program. So all the students in the program have to take simulation. And I want to try to engage all the students. Everybody in that course is not going to be a producer. They're not going to be the modelers. Most of them aren't. So what I want to do is make sure that they are supportive of simulation. And what I've run into is I really need to understand the student challenges. And some of those that I've identified over the years, some directly they'll tell you, I don't like programming. They have to take the course. They took a programming course, but they didn't like it. Or they don't like statistics. Well, those are two important things in a simulation class. And it's not that we shouldn't teach those, but how do we engage the students that aren't programmers or don't like stats? Students also tend to like things that are black and white. They don't like gray area, fuzziness. You know, anything in industry is not black and white. And so it's good that they start to become familiar with that. Logic. I find them struggling just to come up with a structure to build the model. And part of that, I think, is go back, we tend to do less programming, and therefore that helps build logic. Not the syntax, but just building the overall structure and the logic. And if we do less of that, we lose some of that logic. And people. Some students don't like to work with other students, and we do projects, and so they have to. Some of them like to work with people, but they want to pick the people they work with. You don't get to do that again in industry. Understand different learning styles, and we typically teach the way we were taught, or the way we learn. But there's different ways that people learn. A simple example, some people like to see the theory and then see the application. Other people like to see the application and then teach them theory, for example. So there's many others. So I try to understand a little bit about what most of my class is in terms of their learning styles. I think it's important to also address the fact that simulation is not just programming, for example, or modeling, because there's other parts to that besides the programming and the statistics and so forth. To be successful, you have to have communication, you have to have collaboration, you have to be able to abstract that real system and simplify it. And those are different skills. And so different students can bring those skills to a project or to a team, so they start to realize that, okay, I can be in a simulation project and be effective, but doesn't necessarily be the programmer or the modeler. I think we need to encourage continued learning so that they may not want to be involved in simulation right now when they're taking the course, but maybe they realize that when they go out in industry and say, ah, that's a good application. So where can they go to learn a little bit more once they're out of the academic environment? And so to point them to maybe conferences that specialize in simulation, or to websites that you can get a little bit more information, and what types of things are available, say in Flexsim's website, just so they're aware of that. Oops. And then I really want to stress and demonstrate the value of simulation so that they all come out of the course saying, wow, simulation is powerful, and I want to, I may not be, again, the modeler or the analyst, but I think it's important, and I want to be a proponent. And you do that in a number of ways. You can do that with case studies and demos, and projects, and having guest speakers from industry. There's a lot of ways that you can do that and add that into your course. I didn't want to focus on the technical part, but again, to make this complete, and so if you want to have this, I've included, there's the topics, or topics that I would cover in a one-semester course, and the weight, how many classes I spend on it. Now this is kind of oriented towards a totally lecture environment. But I've adapted this. I've taught in programs where there's some lecture and some laboratory time. And I actually like that. But most of the time it's a straight lecture environment. Not saying this is right. This is just what I do and what I think is the way I want to do it. But again, due to the cultural differences and our different environments, our different strengths, our students may want to change that. And I mentioned on there too that that this can also be used in a one of the things I've tried to like to do is to what's called a flipped classroom, where you provide the resources that the students do kind of what you would do in lecture outside, before class. And then the class time is spent on discussions. Because you may do a lecture and the students can easily get 80% of that by some other resource. They can do that outside. But then the 20% that they're struggling with, you can spend that class time, or to go a little bit deeper into the topic. And so that's called a flipped classroom. And I did some of that a little bit later in the some of the courses that I taught later. And what this is based on, again, I'm not going to go through all of these, but these are the course objectives or student outcomes that I wanted to try to meet. And so again, just give you an example of what, in my view, that's what I want to cover. So I've, again, mostly included that just for anybody that wants to look at that. One thing about this, though, every course I teach has a project in it. And so why do we want to do projects? Why is that so important to me that no matter where I teach a simulation class, again, one semester focused on simulation, why do I do a project? Probably a lot of these are probably obvious, is simulation to me is an applied technology. So we ought to apply it. Students ought to have an opportunity to do a project, to experience it. It's a great way to pull together a lot of the topics that you've talked about during the lectures and throughout the course. is a great way also to demonstrate the relevance. Instead of just kind of seeing it or talking about it, they get to experience and say, yeah, wow, this is pretty neat. It tends to engage the students more because they're participating, and most of them like that. And it demonstrates that there are other roles that are important for a successful simulation project. Again, the people skills, or the communicators, or the ones that can conceptualize things, in addition to just the science side, if you will, the statistics, or the actual building of the models and so forth. This is a great way to collaborate with industry. And so it's, again, another avenue to do what I want to do. And it basically enables a better understanding of how things work in industry, how operations, and again, whether the operations is in manufacturing or in a healthcare facility, they start to understand how things work in a more business-like environment. And I think it's important to realize that projects add value regardless of how complicated or big the project is. And in fact, if you're just starting this, I would recommend you start simple and small, just like building a model. I want to start simple and small, and then add as I need to. I'll give you a couple examples of some projects that I've done. I've done a number of them in classes, but it gives you a range of types of things that we can do. And, I guess I need to talk about why not to do projects. Well, they require course time. So if you haven't done projects and you're teaching a simulation class, you got to have some class time dedicated to the project. So now what are you going to get rid of? That's hard times to decide. It definitely is more work. It adds work for sure to do projects in a course. And probably the biggest thing, it adds risk. Projects are fairly risky. So we always try to maybe find ways to mitigate that risk. Well, I think that the benefits that I talked about on the previous slide outweigh these costs. So to take something from Nike, just do it. I think in the long run you're going to be better off. Now, how do we mitigate some of that risk? Planning is probably the biggest thing. Think about your course and where's the project going to come in relative to the topics you're teaching. Certainly do a lot of definition of the project before the class starts, well in advance. You've got to manage this as you go. It's not just assign it and collect it at the end. You need to manage it. And the assessment, I think, is an important part. The one way to help define the project is the kind of classic 5 Whys, 5 W's. Why am I doing this? What is it that I want to get out of it? What are the activities? Who's going to perform them? Where's it going to be performed? A whole long list of those things you need to think about beforehand, and that helps you define what the project actually is. You need to monitor it as it goes on, and I do that by having students do progress reports so that I know that they're progressing or what problems they're encountering before it becomes a crisis. And basically, let the scope of the project or the size of the projects grow or evolve over time. You don't want to start big. So let's take a look at a couple examples. And this one is from a course I taught in Saudi Arabia. I was new to the country. I didn't know anything. I didn't know industry there. So this project is one that I'm the customer, and it's fairly small. It's not necessarily simple, but It was one that was self-contained in the course. An example of the model that they built was they had to design the production facility for a fairly simple 2 products. Building of boxes, but they had to decide how to go from a sheet of material, what had to be done to get to that box, the fabrication and assembly parts, how long does it take. So there was other things in there besides building the model, but then they had to build the model and decide how long things took and how to lay it out and so forth. So there's really a lot there, and it was a real beneficial project. Most of it was done individually. I had a fairly small class, so most of them did it individually, and then parts of it I had where they could work together. And then that was just, again, some of the analysis that they would do. So that's probably the simplest approach, the least risk, really starting out. Another example that I did when I was at Mississippi State, a little bit bigger scale in this case, is we had a real client, a real customer, and that was a regional medical facility. And so they worked with real data, with layouts, and with they visited the site, got tours of it. It was to look at scheduling surgeries, and so they got to visit the facility and so forth. And some other kind of analysis that they needed to do before building the models. They built some kind of interesting simulation models, did the analyses. And I think an important part of this is they then had to present their results to the customer. And what we did is we set it up as like a little fair. The customer, actually the main person that we interacted with was the chief of surgery at this good-sized hospital, and some of the people on his team. They came to the university and walked through and talked to the students and so forth, and discussed the project and what their findings were and so forth. So a really valuable experience, I think. Again, taking a little bit more work, a little bit more risk, and so forth. The last example I actually did here in Poland, or was associated with. This has been going on now in Poznan for probably more than 12 years. I participated in 3 years of projects there. This is a big scale. These are some of the customers. Each student team worked for a different actual client, and they, again, it was a 2-semester course taught by several faculty. The first semester was mostly on logistics design and simulation. The laboratory in that course was learning flexsim. And then the second course was mostly project work, and with typical team size was about 8 students. It was a big event at the university that we had, and I'll show you in the attendees, there would be hundreds of people come to the final presentation. It was a competition to see who could be the best team. And it was judged and so forth, and there were awards. And again, faculty, industry, other students would come to this. In fact, the 3 years I was there, and I think this was probably true in general, is the rector of the university always came to this event. It was a big deal at the university. And, but this is big scale. The types of interaction with industry, number of faculty, number of students, and so forth. So this is not where you want to start. Let me talk a little bit about courses that are not focused on simulation. And I think there's a lot of opportunities here. What I did in this diagram is I took all the industrial engineering courses in our program. And I thought about how are they related to simulation. Now, some are directly related. The programming course, prerequisite. The statistics course, prerequisite. The design course depended on having simulation. So they were direct connections. But then I was looking at all the other courses and how can they relate. And so I think what you can think about doing something like that and then talk to your colleagues and figure out ways that you can get simulation in their class. I'll give you a real quick example. Teaching a statistics course is, instead of having the students for their whatever statistical analysis they're going to do, instead of getting the information from a textbook, have them run the simulation model and generate the data. If it's a neat flexsim model, they're excited. It's a 3D model. They're interacting with that. They don't know how it was built, all of that. That'll come later, but they're exposed to it. They start to see simulation. And if you can do that in a number of courses, then it starts to build that understanding of how powerful simulation is and in the student's mind. So I think what we have to do is how do we do this? And looking around at colleagues and figuring out ways that we can get students involved, get simulation involved in other classes. A question often comes up, well, they haven't had the simulation class, how much do they have to know? My answer to that is not very much. They have to know something. But I think we can cover the basics of what they need to understand in maybe a short document. Could do a lecture, but I think a document or a video or something that they could basically be exposed to and get enough understanding to basically use the simulation in their other classes. I think again, one of the things we're going to hear from today is gaming, and I think that's a great opportunity to do this, is to find places in other parts of the curriculum that we could use gaming, which is getting them into simulation. I'm going to go through a couple examples just to show you what I'm talking about. This happens to be an example that's out of our textbook. One page, description, and that's the model. Maybe you probably may have seen that. It's a roller coaster. Everybody knows what a roller coaster is, and so they don't have to understand how a hospital works or how a manufacturing facility works. They know this. Real simple interface. The things they had control over, the number of cars, the number of people per car, and how many people work at that roller coaster over the day, because the demand changes. They ran the model as many times as they want. They come up with one recommendation. They turn that in, and then we compile the results and plot against two performance measures. One is the wait time, and one is profit. And what we can find is that basically these solutions dominate all the others. So the people that come out and provided these, what we call the efficient frontier, are, quote, the winners. But then you're left with, there's no one right answer, because it depends on how you balance profit and wait time. People waiting to get onto the roller coaster ride. And so that becomes a judgment call. And so again, a quite effective learning tool. We actually used this example in our freshman level Intro to Industrial Engineering course. And students really liked it. So they got exposed to simulation first year. Another one is a little bit more involved in terms of, it's not one page, I don't remember how long the actual document is, 10 pages maybe, something like that. Again, a small model, it's not really that simple. It's a copy shop, a small copy shop. And again, a simple interface, but there's a lot of things you can change on there, a lot more than the roller coaster. Change distributions, you can change the number of people that are serving, the characteristics of people. In other words, if you balk, that means you come in and you go, oh, the line's too long, and you leave. So you can model that behavior, as well as what's called reneging. So I get in line and I'm waiting in line for the server, and I'm saying, I've waited too long, and I leave. Okay. So a little bit more realistic example than just a simple queuing example. Provides them with dashboards that are already pre-configured to give them the results that we think is important. And it can actually, it's set up to run a multi-scenario experiment. I think there were 12 options that they could look at and consider and understand the effect of those changes. Again, requires very little knowledge of actual simulation. I want to change gears now and talk about research. A couple examples of research, again, to give maybe some different ideas and the range that you can do and how you might link that to either teaching or some industry work. The first one is related to the triangular distribution. Most of us know what that is. It's great distribution for simulation because, especially without data, you need 3 parameters: minimum, maximum, most likely. That's great. But there's sometimes that somebody says, yeah, but I've had a lot of data. I know a long run mean. Or I know this, I have an idea how much variability there is. So what we did is we said, okay, you need, for the simulation model, you need to provide min, max, and most likely. But you could also provide the mean, the standard deviation, or how much skewness there is. So that has 6 parameters, and all you needed to do is specify 3 of them. So if you said, well, I know the mean, the standard deviation, and the skewness, then we can tell you what min, max, and most likely are. Okay. And that's basically done through tables. We've set up some tables to make it easy to figure that out. The other thing that we found, especially in industry, is that people, when you ask them for the min or max, they don't like to give you that. You know, that sounds too extreme. How do I set that boundary? What people are more comfortable with is saying, well, I can tell you kind of the minimum, somewhere where maybe 5% could take less time, or 10% could take more than the maximum. Well, that's fine. Just tell us that you think 10% takes more than 20 minutes. Okay. And then give us the same thing on the lower end, and we can generate what those extreme points are. Okay. That then you need to put in the simulation model. So again, a little bit more theoretical, especially looking and sounding, but it's, and we did a little application that you could, a little visual basic application that you have tables, or you could just enter some of those parameters. But again, it can be used, it's used a lot in practice, and it's good you can bring it into the classroom as well. The second one is, again, maybe a little bit more theoretical in a way to start with, is a lot of ways. This happens to be in a cross-docking facility. Colleague developed mathematical programming models, integer programming models, to determine the schedule for when trucks arrive. Well, one of the problems with mathematical programming problems is they most of the time, don't consider variability. So how does it perform in a simulation model? Which is kind of how it would perform in reality, because things are really variable. So that's what we used simulation for, is to test their algorithm. And it actually led to defining what is robustness, because you want a robust schedule. And then how could they change their programming to make it more robust? So it gave a really good test bed to do that. Again, looks somewhat theoretical, but it, again, has practical applications. Another one, and this is mostly a little bit more applied. All of these have been published in at least conference proceedings. So you got at least you get the research part or the publication part, scholarly part. I've used them in class, some of these in classes for the students to understand applications. And of course, especially these are much more industrial based. This is one where in a very large shipyard that makes a variety of military ships at the same time, different types of ships. Everything has to go through one shop. That's the bottleneck in the yard, in the whole shipyard. And it may be a little bit hard to see there, but the variability, that's, if you said, here's a sequence, that's how much time it would take at each of those positions as it goes through that operation. And so huge amounts of variability. And what they wanted to do is increase the throughput. So what we did is we built a simulation model, and we actually built an optimizer using evolutionary strategies to sequence, to look at what's the best sequence to produce. And we found about a 10% improvement in throughput, only by changing the sequence. No investment. They liked it so much, they said, great, we want to use it on the shop floor so that we can determine if something gets out of sequence, then how do we resequence? So we put this in a decision support system and made it available basically for shop floor use and not having to understand what's going on behind the scenes. And then the last example is a fairly large-scale project for the U.S. Navy. We modeled their logistics network. And you might say, well, doesn't the U.S. Navy have models of their logistics network? Yes, they do. The problem was the contractor wanted to use this to decide how to design supply ships. So they didn't want to run these giant logistics models. They wanted something quite simple that would give them the trade-offs of things like, do I make a few big ships? Or do I make a bunch of small ships? Or how do I decide what resources go on what ships? Should they each be dedicated to a resource, or should I have ships that have everything they need? So we had to model the logistics network, where the different battle groups would be traveling, where the supply ships would be, when the battle group needed something, how long did it take for the supply ships to get there and fulfill their needs. And this was not built on the new interface. I wish I had the new GIS component in Flexsim. This was built way before that. But again, basically built on a map and provided them with guidance on, again, how to, at a high level, what's the ship design. Just to mention a little bit about industry collaborations. Again, I think they're real important. I hope you've seen some examples where I tried to bridge that today with teaching and research activities, as well as directly being funded through industry. And again, I think, I'm not going to go through these, but industries have needs. They certainly need, they need problem solvers. They need people to come in and take a fresh look, technology transfer and so forth. So they've got a lot of needs. Education's got a lot of needs. They want relevance for the students. They may get funded to do some of this work, a variety of things. Both have needs, and simulation can be a way to satisfy both of their needs. You do have to kind of think about some balance on this. I mean, there's obviously a tremendous amount of benefits, but we have to understand that this adds uncertainty. Again, it's anytime you're working with two different groups like that, there's risks and uncertainties and other kinds of issues. And the academic world and the industry work at different time frames and different priorities, and so you have to deal with those. You just have to be aware of it. You can deal with it. and also how the students, most of the time students really like this, to collaborate and work on industry projects, and most of them do. So a few final thoughts. Let me just wrap this up kind of quickly. And so what I hope you saw is that you want to find synergies between teaching, research, and service, or working with industry collaborations. Stephen quotes something from Stephen Covey. I think that's really important, not only to projects and things like that, but even modeling, is begin with the end in mind. That means, what is it that I want to accomplish? What's the end? And then figure out how to get there. Don't start defining what the paths are and not sure where you're going. Start small. I'm a big believer in that, and certainly in modeling. And add complexity and size as you need to. And plan. Again, consider the consumers as well as the producers. Build proponents. Model what you need, not what you can. Okay, just because I could get a sophisticated model, do I need that to solve the problem at hand? And kind of the 4 Ps of simulation, or at least from my look at it, is what is simulation for? It's for problem solving, so keep that in mind. It's a process for improvement. Simulations are projects, so manage them like projects, whether it's in your course or in your industry work or whatever, or even in your research. And then simulations are performed by people for people. So again, you've got to interact with people, and so collaboration is a key to success. Well, kind of wraps that up. I certainly want to thank you for your attention. I hope that I met the goals, that gave you maybe some ideas, and you want to generate some discussion, and hopefully that will lead to collaboration. And I'm going to end with a quote from Henry Ford, that basically, coming together is a beginning, staying together is progress, and working together is success. Again, thank you very much.